Good morning, everyone. I've been asked to go through some problems of digital systems, that is COE328 of TMU, and it's a bit too close to the final for me to do a tutorial, so I decided to do a pre-recorded video. Let's start with the different types of flip-flops and latches you'll be seeing. The first one is the SR latch. The SR latch, has the set, reset, and the out not. Sometimes it'll be described as this. The way that we do it is with the hat on top. This one is very simple. It's in the name. It is a set and reset latch. If set is 1, Q will be 1. If reset is 1, Q will be 0. Q naught is obviously just the not of Q. So sometimes you can just omit Q naught if you're not using it. It's effectively the exact same thing as SR, Q, and then you have a naught here. This is your Q naught, right? Naught. Nothing surprising there. You will also have the gated SR. The gated SR has 3 inputs. You have the S, R, and in the middle you have the clock. And so this acts the exact same way as the SR. The only difference is that nothing will change until clock turns on. So this is the SR clock gated SR. Set, reset. It's in the name, right? And then there are 3 other ones. These ones are all flip-flops. The first one is the D flip-flop. You'll have a D and a clock. Or this will be the clock. And this just means that things will only change when you reach the edge of the clock. So if I have the time diagram of a clock, it goes up like this, down like this, up like this, down like this. It only activates, it only does something at this point. If something changes in between, nothing will happen. It's only on the edge. This is called edge triggered because actions only occur when clock changes, not when it maintains a value of 1. So you're going to have D, and then Q naught. All of them will have Q and Q naught. This is D flip-flop for data. All it does is it copies D to Q. That's it. So if D is 1 and it is activated, Q will be 1. If D is 0 and it's activated, Q will be 0. That's it. The second flip-flop is the T flip-flop for toggle. You can probably already guess what this does. You have the T, you have the edge, Q, Q naught. When what do you say? When this flip-flop is activated, if T is 1, Q will be inverted. That's it. If T is not 1, then nothing happens. So it toggles the flip-flop. If toggle is 1, it toggles on the edge. When it's activated on the edge, same thing. The next one is the JK flip-flop. The JK is probably the hardest to remember because JK doesn't actually stand for anything. It stands for the inventor's name. His initials were JK. It is identical to a SR latch. However, first of all, it's edge triggered. However, you might notice here we have if reset is 1, Q will be 0, and if set is 1, Q will be 1. However, what happens when both of them are 1? In an SR latch, this is considered undefined. Basically, if both of them are on, you are doing something wrong. In JK, if both of them are on, it acts as a T flip-flop. So if if J is equal K is equal 1, or if J is equal K, really, it acts like a T flip-flop, right? If both of them are 0, nothing changes. If both of them are 1, it toggles. So now we have all of the different flip-flops and gates that we will be seeing in this course. To explain the diagrams of a circuit, I'm going to be using this example circuit to basically derive them all. So we have an example to show off how they work. Let's start with the state assigned table. So we have 4 variables here. We have Q1 and Q2. These are the outputs of our flip-flops. And then we have our next state, Y2 and Y1. Let's actually, let me do this. Y2, then 1, and Q2, Q1, Y2, Y1. So you'll notice that Y1 is before Q1. So if we can determine Y1, because this is a D flip-flop, once it is activated, Y1 will be copied into Q. So we can determine the next state of the machine. Let me show you. Let's write a table of possible states of our machine. Our machine can have both of the Qs be 0, Q1 be 1 and Q2 be 0, Q2 be 1, Q1 be 0, and both of them be 1. And we have one input, X. Let me move down so we can see what happens when X is 1 and when X is 0. Actually, let's flip these around. There you go. X is 0 and X is 1. Because our output will change depending on that. Now, there's 2 ways we can solve this. We can either figure it out one by one and go through the logic, or we can create an algebraic equation, and then we can quickly solve it. Let's take a look at Y1. What is Y1? Y1 is going to be a set of ORs. We have 3 inputs here. One of them is X, right? X goes directly. Let me use red here, actually, so that it's clear to see. One of the inputs is X into this OR. One of these inputs is not Q1. You can see here. So not Q1. What is this other input? Let me just draw that there. What is this other input? This is going to be Q2. So Y1 is X or not Q1 or Q2. What about Y2? This is Y2. We have a NAND gate. So immediately we have 2 things multiplied by each other, knotted. The first value is Q2. The second value is X. Oop. That's my previous tutorial, I think. So let me rewrite that a bit better. There you go. Now we have algebraic equations. Instead of needing to check over this circuit over and over again and do logic, we can just do some quick maths. So let's look here. This is the state assigned table, by the way. State assigned table. So Q2 is 0, Q1 is 0, and X is 0. What is going to be Y1? It's going to be 1, right? Because 0 plus 1 plus 0. What about Y2? Q2 times X, both of these are 0, so it's going to be 0, knotted 1. And I hope you know how to do this. So once again, we have X1, Q2 0, Q1 0. That's going to be 1, 1, 0. That's 1. Y2 is still going to be 1. And you can start moving your way down. I'm going to go skip this part because you should be able to figure this out. So we have a lot more ones and zeros. And once again, for each one of these, for example, X0, Q2 0, and Q1 is 1. We can, wait, did I do this wrong? Oopsie. No, I'm right. So Q2 is 0, Q1 is 1, and X is 0. That's going to be 0 plus 0 plus 0. You get 0, right? So this is our state assigned table. We have our current state, and then if X is 0 or X is 1, you move on to the next state. So here, let me move this down just to right on top. State assigned table. This is the current state. This is going to be the next state. Well, technically, it's still the current state, but these Y2 and Y1 will become Q2 and Q1, thus the next state, right? All right. So now let's do state table. State table is very similar to state assigned table. However, instead of putting it in binary, we assign each one of these values a state name. Usually, it becomes S0, S1, S2, S3. And just to make things even easier, we just, these numbers here are just a binary equivalent. So 0, 0, 0, 1, 1, 0, and 1, 1. These don't line up. Oopsies. So you end up with actually the exact same table as state assigned table. Just instead of writing it in binary, you write using these states. So let's do that. We have the current, next, this is Q2, Q1, Y2. Oh, sorry. This X is equal 0. X is equal 1. Let's move this down. Y2, Y1, Y2, Y1. And we just replace this. It's going to be S0, S3, S3, S1. This is S2 and S3. S2, let me just fill this out. S2 is going to turn to S3. This is S1. Again, 0, 1, S1, S1. That's it. And then finally for S3 here, we have S3 and S1. One of the notable things you'll see is that it is impossible to return to S0. None is impossible to have any state that will give you S0. All right. And now we can draw the state diagram. for this, let's draw each state as a bubble, so to speak. And now we simply draw the arrows of where we're going. So in this case, let's start with S0. S0 is going to turn to S3. So we could just draw a straight line. The inputs do not matter. It's just going to go to S3 the next time. Now, S1. If X is 0, it's going to go S2. Let's draw that. So it's going to come across if X is equal to 0. Now, if X is equal to 1, it's going to go to S3. Take a look at S2. Now, if X is equal to 0, it's going to go to S3. X is equal to 0. And if S is equal to S, or if X is equal to 1, it goes to S1. You can curve these out a bit more if they get too close. It doesn't need to be a exactly straight line, of course. Now, if you have S3, if X is equal to 0, it returns to itself. And if X is equal to 1, then it goes to S1. Or, yeah, S1. I'll have to redraw this here. This is going to be X is equal to 1. This is X equal to 1. And now we have drawn our state diagram. I'll show you a bit more because this state diagram, how you draw it changes ever so slightly when you are dealing with a Mealy state machine, and I'll discuss that in a second. We're just working with a Moore machine, so you don't need to do that. And once again, I'll cover Mealy and Moore in a bit. Okay, so now the question is asking us, well, not the question, but well, kind of, but anyway, to draw the waveform. So, a couple things need to be noticed. The first one is that all of our flip-flops are on the rising edge, and I failed to mention this because I'm a little stupid. If you see a dot in front of the edge trigger, so let me go back to the first I was drawing here. So say if you see something akin to this, this is a falling edge trigger. Let me just draw that over here. When you see this, this means it activates when this value goes from 0 to 1, right here. When you see dot followed by that, that means a not, right? So it activates when it falls from 1 to 0. Keep that in mind. However, in this case, we only have rising edge triggers. So, once again, let's fill this out. And so we are going to start our state at 0, 0. Okay, so if we're here, as you can see, this is not clear, by the way. I don't know why it's written like that. This is not clear. So interpret it opposite. This is 0, this is 1. Therefore, clear is on. And therefore, nothing will be happening at all. So let's draw that out until the end of that clear. Over here. Now, if Q1 is 0 and Q2 is 0, what is Y1 and Y2? You can look over here. Our X is 0, right? 0 and 1. So they're both going to be 1. So for this length, Y1 and Y2 are going to be 1. Now nothing's going to change because, once again, clear is on. Right? And now clear is off. So now things can change. We just need to wait for the rising edge, because again, things don't change for flip-flops unless the unless the flip-flops are activated. So these Q1 and Q2 are going to remain constant, and so is Y1 and Y2. Now what happens at this point? X is 0, clear is 1, or clear is 0, so things will happen pretty much. And we're on the rising edge. So Y1 and Y2 get copied to Q1 and Q2. Oop. Right? Because they're D flip-flops. Whatever's in Y will be copied to Q on the rising trigger. So now Q1 and Q2 are both 1. What happens to Y of 0? So at this point, right here, X is still 0. So Q1 is 1, Q2 is 1, and X is 0. Let's see here. Q1 and 2 are both 1, and X is 0. So they'll both remain as 1, 1. However, X changes at this point. So it only maintains 1 up to this point. Now X changes to 1. Now what happens when we have Q1 is 1, Q2 is 1, and X is 1? Once again, we look back to our state assigned table. It's going to be 0, 1. Y2 is going to be 0. So Y1 is going to remain high, and Y2 is going to drop down to 0. I'm sorry, I wish I had a better grid, but I don't. And again, Q1 and Q2 is really not going to change until the next rising edge. So we can actually just stretch this out until the next rising edge. Let's extend Q1 and Q2. Okay. Now what happens at this point? X changes back down to 0. Well, this is the same as this point here is going to be the same as this point here. Q1 is 1, Q2 is 1, and X is 0. So we can just return back to what it was before. Both were high. Or you could just look at the table. They'll both be high. Oh, not all of the way. Once again, X switches to 0 or to 1. So it goes high. And then X switches to 1. Y2 is going to come back down according to our state table. Once again, you just look at state table. X is 1. It's going to be 0. And Y1 is going to remain at 1. Now, once again, we reach clock. We reach the rising edge. And now we copy whatever's in Y1 and Y2 to Q1 and Q2. So Q1 is going to copy Y1. It's going to remain at 1. Q2 is going to copy Y2, which is low or 0. So it's going to drop down. See? All right. And once again, Q1 and Q2 aren't going to change until the next rising edge. So we can just extend that out. There you go. What about Y1 and Y2? Well, now Q1 is 1, Q2 is 1, and X is 1. So Q2 is 0, and X is 1. So Q1 is 1, Q2 is 0, and X is 1. What do we get? We get 1 and 1. So this is going to remain 1 until something else changes. What is the next thing that changes? X again changes. So we can draw this as 1 until something changes, right? Because then we have to reevaluate. Has something else changed? Y2 is going to return to 1 according to our table. Now X drops to 0. So now we're going to have Q1 is 1, Q2 is 0, and X is 0. Q1 is 1, Q2 is 0, and X is 0. We have Y is 1, or Y2 is 1, and Y1 is 0. So this is going to remain at 1, and Y1 is going to drop down to 0. Now we hit the rising edge. Once again, we're going to copy Y1 and Y2 to Q1 and Q2. Q2 is going to, once again, let's draw the, and they're going to stay that way until the next rising edge. Q2 is going to rise up to 1, like so. Q1 is going to drop to 0, like so. What happens to Y1 and Y2? Well, let's look here. Once again, draw your borders whenever your inputs change. So at this point, X is 0, Q1 is 0, and Q2 is 1. X is 0, Q1 is 0, and Q2 is 1. You're going to have 1 and 1. So Y1 is going to be 1, and Y2 is going to be 1. Now X has changed. X is 1. So Q1 is 0, Q2 is 1, and X is 1. Let's look at the same thing there. Q1 is 0, Q2 is 1, and X is 1. Y2 is going to be 0, and Y1 is going to be 1. So Y2 is going to drop down to 0, and then Y1 is going to remain at 1. I hope you could start seeing the pattern now. Once again, we hit the rising edge. We copy Y1 and Y2 up until the next rising edge over here. I'm just going to complete this for completeness' sake. But I would recommend you stop here and do the rest yourself, see what happens. All right. X is going to be 1 here. So X is 1, Q1 is 1, and Q2 is 0. So if I'm correct, yeah. Q1 is 1, Q2 is 0. Yep. So both of them are going to be 1 up until X changes. And then we need to reevaluate, right? All right, now X is 0. Once again, we come back here. X is 0, 1, 0. 1, 0. Y2 is 1. So Y2 is going to jump up. Sorry, 1 sec. One second here. My bad. I just realized this part here is wrong. This should be 1 and 1. There you go. There you go. Right, because X1 is 1, Q1 is 1, and Q2 is 0. Both should be 1. Anyway, Y2 is 1, Y1 is 0. At this point, the rising edge is triggered, and Y1 and Y2 is copied into Q1 and Q2 up until the next rising edge. So Y1 is going to be copied. It is low, so Q1 is going to drop low. Y2 is going to be copied into Q2, so it's going to rise up to high. Okay, so what's X? So Q1 is 0, Q2 is 1, and X is 0. Yeah, so 1, 0, 0. So here. So both will be 1. Both will be 1. Both are going to rise up to 1 or stay at 1 in Y2's case. And now x is 0, or x is 1. This here, and let me just clear up all these circles. There you go. 0, 1. Y2 is going to be 0. Y2 is going to drop down back to 0. Y1 is going to remain at 1. And, oh, these should extend all the way to a rising edge, and we've hit the rising edge once again. These are going to be copied. YQ is going to go up until the very end, and Y2 is going to, Q2 is going to drop down to 0. Once again, Q1 is 1, Q2 is 0, x is equal 1. One and 1. There's your waveform. It is simply an application of the process. Now, one thing I did kind of fail to mention was regarding output. So this one's very lucky in that the current state is the output. But suppose there was not an output, or the output was different, right? Well, we just add a new output here, and we put the bits in. Say say it's a 4-bit output. We can assign each state an output. It's same thing with state table. You put the bits in here because it's not a state really. For the I'm just gonna put this in red as a sample output. It also applies to the state table. Same sort of thing. You just put the bits in because it's we don't give it exactly state. I said that poorly. The output is not defined in states. We define it in bits, as far as I'm aware. For a state diagram, all we would do, so state diagram with output. This is for a more only. I'll show you how a Mealy state diagram works. You're going to have the state here divided by the output. I have to draw it a bit wider. Bit fat. S0/1101, for example. So if the state is S0, the output's going to be 1101. Likewise, you would just add some extra states here. We can define output 1, output 2, output 3, output 4, that sort of stuff. So now you know the 4 different ways to represent a circuit. 5 if you count, if you count the algebraic way. So I mentioned Moore and Mealy a lot. And frankly, I should have answered it a bit earlier than I'm doing right now. It's a very simple concept, right? Moore machines, the output is purely based on state. So the input only decides next state. All right, you follow me? So if a Moore machine has a state 0, it's going to have the same output. Let's define that as output 1, right? If state is 1, it's going to have output 2. It'll never change. You know that if you have a certain state, you're going to have a certain output. I guess a way to look at it in a more like digital systems way is that for a Moore machine, output takes in state and it gives out the output. So for one state, you're getting one output. One state, one output. Now, for a Mealy machine, output, both depends on state and input. So likewise, yeah, that's correct. So input only decides the next state for more. It doesn't affect the output. For Mealy, the input does affect. And state. So as an example, with a Mealy, you take in both the state and the input, and you get an output. You'll remember that for this one here, if we treat Q1 and Q2 as our output, which they are, right? Because if you look in our original diagram, Q1 and Q2 were our outputs. They're also our state, right? So if you know the state, you know the output. Pretty simple. And they only change on the rising edge. That's why it's our state, because it sort of remains the same state until we reach until the flip-flops are activated, so to speak. In a Mealy machine, the output can change in between clocks. Let me see if I can grab an example. Actually, let's make a stupid simple example. 1 second. Behold, a stupid simple example of a Mealy machine. You'll note that our flip-flop defines our state, right? But output is not only decided by our state, but also our input. Let's draw a little state table for us. So state assign table. So we're going to have our state. We're going to have our next state, or current, our next, and then our output. So for our current state, we only have Q. It's going to be either 0 or 1, right? This is Q. This is going to be Y. For our next state, if in is equal to 0 and in is equal to 1. Wait, oopsie. Yeah. So we're going to have our Y. So what happens when our in is 0? Well, it's just going to copy it, right? It copies Y to 0. It's just going to be in, right? So it's going to be 0, 0, 1, 1. In determines Y, right? Y is equal in. And for output, okay, now we have to also take into account our inputs. What happens when let's hear out. Sorry, I should be using like single letter variables, but whatever. So if Q is 0 and in is 0, nothing happens. If Q is 1, or if Q is 0 and in is 1, still nothing happens because this is an AND gate. Now, if Q is 1 and in is 0, it's still going to be 0. AND gate, right? Out, out is equal Q times in. Both in and Q need to be 1 for an output of 1 to happen. You see this? So our output is determined by both our state and our input. Let's draw a Mealy state diagram for this. Now, Mealy state diagram is a little different. You remember how I said in the more diagram, if we have an output, we draw it in the circle. However, the state no longer determines the output. The state and the input determine the output. So in this case, we're going to draw our state. So our state 0, let me just draw S0, and our state 1. And this is a little different because states don't really lead to each other more than they're just assigned. But we're still going to draw it like a state machine, you know? So let's take a look here. If Q is 0, so we're starting at state 0. If in is 0, it's going to return to itself. And here we're going to write 0, that is our in, right? Slash our output. So in is 0, it's going to be 0. You see that? This is in, this is out. Now, if in is 1, it's going to go to state 1. So 1, and the output's still going to be 0. Now, at state 1, I drew this way too close. Oopsies. Let me move this down a little. At state 1, if in is 0, it's going to return back to state 0. And our output's going to be 1, so 0, 0. And if our state is 1 and our input is 1, it's going to return to itself. The input is 1, and the output's going to be 1. So this is a Mealy, what is this called? State diagram. I hope this video gives you a sort of quick or maybe not so quick overview of the different tabling and diagram and waveform systems we do to represent a circuit. That being said, I hope you all do well on your final exams and have a good day.